So in the first video in this series, I gave you a quick overview of what are the issues in doing automated reasoning in particular mathematical logics. And now I want to give you some of the details of how to do this work in first-order logic. What's the simple mechanical algorithm that you need in order to do proof by refutation in first-order logic? So I'm going to take this in two steps, and this video is just going to cover the process of normalization. And I should also mention I'm going to give you a certain syntax, the syntax of the language I use called suo-kif, standard upper ontology knowledge interchange format. It's the language in which sumo is defined in. And I hope to do also two corresponding videos, one for the TP-TP language and maybe also one for a sort of standard textbook first order logic or predicate calculus, but we'll see. Hopefully this one is also reasonably understandable for most people. So what is normalization in first order logic? So it's a process of reducing the number of symbols in the language to a small set that is strictly logically equivalent through a mechanical, repeatable mechanical procedure, something we can turn into an algorithm. Now, there are lots of different algorithms for doing this kind of normalization. There are other normal forms, too. There's not only conjunctive normal form, but there's disjunctive normal form, and there's also prenext normal form. I'm just going to talk about conjunctive normal form. That's the one that's most commonly used, but there are these others. And I should also mention that because there are different algorithms, these different algorithms can have different, but importantly, logically equivalent results. But just because they're logically equivalent doesn't mean they're performance equivalent. So you can get different normalization routines which can result in longer or shorter expressions that are logically equivalent, and that can have a big impact on performance. So choose wisely if you have ambitions to develop a world-beating theorem prover. I'm just going to talk about one simple one that's also in Russell and Norgevig's classic Intro to Artificial Intelligence textbook, now I think in its 10th edition, so it's definitely withstood the test of time. So conjunctive normal form. In conjunctive normal form, there are only three logical operators, and, or, and not. But traditionally, first-order logic has not only those three, but it also has implications, which is a sort of if statement, as one way to read it. If A, then B, or if A then B is the same as, A implies B. We also have if and only if, IFF, which can also be expressed in some syntaxes as this double arrow. In suo-kif, we use the single arrow and the double arrow for implies and if and only if. And I also mentioned equality. That's a pretty important thing to have, as well as quantifiers. This is really what probably most people remember from whatever introduction they might have had to predicate calculus as a first-year graduate course or something similar in college if you're getting a STEM education. And there are these two quantifiers, forall and exists. So for all x such that x has the following attributes, or there exists an x, at least one, that has the following attributes. That's how you read these two quantifiers. Hopefully you're already somewhat familiar with these, or otherwise this may be a little mysterious. So I've got some other videos on learning logic that if this isn't familiar, take a look at those and hopefully that will help. So why conjunctive normal form? Why do we want to bother with this extra step? Can't we get right down to inference? Well, we could, but then we'd have an inference algorithm that's a lot more complicated. So pretty much all of the major first-order theorem provers do this kind of thing in some form or other for at least some of their work. The core algorithm of refutation theorem proving relies on having this simpler language with only three operators, and then the algorithm is somewhat straightforward at least. So it also has this additional benefit that by removing some of these extra operators and changing a statement into a different logically equivalent form, a lot of the time you get the benefit that things that are stated in different ways turn out to be syntactically equal as well as originally logically equal. So it's a form of canonicalization or normalization, that same sense of the word that you get in other disciplines of computer science and mathematics. So here's the algorithm. It's only 7 steps. We'll go through each of those steps, and we'll start with removing implications and equivalences. And if you looked at some of my prior videos, I've got some detail on this, especially doing truth tables to sort of help prove to you that each of these logical equivalences are in fact valid, that they're valid to have in a proof. We can use truth tables to do that. So take a look at some of the prior videos. I'll link them down below in the comments as well. So first step, remove equivalences. Remove if and only if. So if and only if AB is the same as the conjunction of A implies B and B implies A. So that's why the arrow goes both directions. So that's an easy first thing to remove. And then we actually want to get rid of implications entirely. And one thing that I'd described in one of these prior videos, one on learning logic, was showing you the truth table for how to convert or why it is valid to convert A implies B into not A or B. So here's the resolution of that. Here's how you implement it. Just take A and negate it and put it in the disjunction with B. Easy. The next thing you want to do is move negation inwards. Oh, and by the way, up in the upper corner, it's this other video, Ontology Talk, Paraphrasing Logic. That gives this discussion of truth tables. It's part 2. Again, I'll link it down in the comments. So moving negation inward, also discussed this in that same video, this notion of you have to flip your quantifiers and flip your connectives as you're moving these negations inward. So if you have P or Q and you negate it, and you want to move that negation inward to do this part of the algorithm, you actually flip the or to an and. And so that's why you wind up with and, not P, not Q, or said another way, not P and not Q. So you've moved that negation inward, and in the process you've flipped your disjunction or to a conjunct and. Similarly, the other way around, if you have not P and Q, then you flip the and to an or, and then you push that negation inward. Same thing happens for existential and universal quantification. So you push in the negation, forall turns into exists, or exists turns into forall. And then the last one should be obvious. Double negative is equal to a positive, so the nots cancel each other out. So not P is the same as P. So you can try any of these with truth tables also. Next thing to do is standardize variables. So this hopefully should be clear to anyone that's been doing some programming. Variables have scope, and the scope of a variable in a quantifier is that of the quantifier. So in this first statement, we have for all x, p of x, and then we also have exists x, q of x. Well, these are different variables, question mark x. They are different, right? Because there's two different scopes. There's the scope of the forall, and there's the scope of the existential, the exists. And they're different scopes. So therefore they are different variables. So to make sure we don't confuse things for the algorithm, we make them distinct. So on the left, the x in the existential turns into a y in that same existential on the right. So we're standardizing the variables. We're making it clear that variables in different scope are syntactically different variables as well as just semantically different variables. We also want to move the quantifiers left. So if we have a universal quantifier, the forall, that's embedded deep in some complicated statement, we can pull it out. And the reason we can do that is because we've already standardized the variables, right? If there was a scoping issue, we'd have to worry about is that x going to conflict with some other x in the statement. We've made sure that if it's a distinct variable, it has a distinct name, so there's not ever going to be a problem with pulling it to the outermost scope. So we take this for all x that's kind of in the middle of the statement, we can pull it to the outside, and we're left with p or q of x. Skolemization. Now, this one is pretty counterintuitive, really, and causes, I think, all of us some problems when we're learning it. So it's the notion of if we have an existential statement that we want to get rid of, what can we do with it? We want to create essentially an identifier that is unique. Because exists just commits us to there exists one or more of something, and we just want to make sure that that thing doesn't conflict with any other thing or symbol in our symbol system. So we create a function called a scolem function, and we create that function and we pass the argument of any other variable that occurs within the scope of that particular existential expression. And so here we can say that if we have this question mark x, and the scope is the entire statement, that when we convert y to a scolem function, it's in terms of x is one way to say it. So you can see that over on the left, the h of question mark y turns into h of scolem function question mark x, because the x is within scope of the y. So that's the mechanical process. I don't really have a better intuition than that to give you. So if that doesn't fit at the moment, if it doesn't resonate with you, well, hopefully you can just take my word for it as a mechanical process, because that's ultimately all this is. It's just a mechanical algorithm that's been proven to be truth-preserving or accurate. So the next thing to do is to distribute and over or. So here's an example. So if we have or of A and B and C, so A and B or C is a better way to read that, then we can pull the A out of it. We sort of distribute the C over this. So we wind up with the and of A or C, B or C, or A or C and B or C. And you can try this with a truth table and prove it to yourself that this is true. The last thing we do is also pretty easy. So we're going to flatten the disjunctions. So A or B or C is logically equivalent to the second one, A or B or C. It sort of falls out if you actually read it in English. It's pretty obvious. All right, so you can also try this one with the truth table. So now we're done. That was the 7-step algorithm. Each of the steps are fairly simple. To write the algorithm takes a little time to handle all the different cases, to handle recursing down these nested lists. But it's really not that hard. And so there are lots of these algorithms. And it's just the challenge is which one do you use and making it as fast and efficient as possible. So that's it. In the next video, I will talk about the actual logical inference, automated theorem proving using the refutation theorem proving method. And I hope this was useful and understandable to you. If so, like, subscribe, and comment, and thanks for listening.